Now, what is matter made up of? What is its primary composition? If you'll turn with me to page 227, we're going to look at the composition of matter. Well, it's made up of elements. These are the fundamental units of all matter. Okay, these are the fundamental units of all matter. Now, these things are found on the periodic table of elements. If we were to look over at the periodic table, and I don't have one here with me, but if I did, I could show you. A periodic table is a list of elements in a box or rectangular type form, and these elements are listed according to their size, each one having a number at the top left hand corner known as the atomic number. They're also going to have a number listed at the very bottom, usually the bottom middle of that element, known as the atomic mass. Okay, they are organized according to their atomic number. Now, atoms are the building block of all elements. Now, we are looking at 4 basic elements right there in front of us: carbon, oxygen, hydrogen, and nitrogen. 96% of the body is made up from these 4 elements. Now, there are other elements that our body uses, but they are known as trace elements, and they are a much, much lower percentage. You're talking about less than 2 to 3% may be made up of these trace elements. But let's look at some of these elements real quick. If you'll turn to page 28 in your book, there's a table there, and you're going to see the very first element that is mentioned is oxygen. 65% of our body is made up of oxygen, a major component of both organic and inorganic molecules, as a gas essential to the oxidation of glucose. That means the breaking down of glucose to create, or I should say to develop, the high energy molecule ATP. Carbon. It is the primary element in all organic molecules, including carbohydrates, lipids, which are fats, proteins, which are the building blocks of all cellular function, and nucleic acids, which are what are found inside the nucleus of your cell, and is what our DNA and our RNA are made up of. Those are nucleic acids. So carbon is essential for all living things. Hydrogen might be the most abundant, actually is the most abundant element in the solar system, but on Earth it's not. But in your body it's about 9.5%. It is a component of most organic molecules as an ion. That means it either has a positive or negative charge. It influences the pH of body fluids. Now, what is pH level? We're talking about acids, acidity in your blood system versus basicness in your blood system, meaning the difference between being an acid and a base. And we'll talk about that later on in this chapter. Now, all the rest of those components, except for nitrogen, nitrogen is a component of proteins and nucleic acids. It is a very strong component of genetic material. It is absolutely essential for us to be able to run any of our cellular functions, to give intelligence to our bodies. Nitrogen is absolutely essential. Nitrogen is also probably the most abundant element in our atmosphere here on Earth. But that's found on page 28. Now, subatomic particles are what make up all atoms. The nucleus of every atom has 2 primary particles in it: protons and neutrons. Okay? Protons and neutrons. Now, if you'll turn on page 29, you're going to see a little table at the very top, 2.2, that kind of shows how things are broken down. Protons have a positive charge, whereas neutrons have 0 charge. They don't have a positive or a negative charge. They are 0. They are neutral in their state, and that's going to be important later on because it does affect how some atoms are built. Now, outside the nucleus of the atom, you have these smaller particles that are orbiting around it at the speed of light. and we can't really measure exactly where they are because they're moving so fast, and we can't exactly tell how much they weigh. You can calculate it, but we're not going to get into that because that's a little bit more advanced than what we need. But they pretty much don't make very much of a difference in the weight of the atom. That's why when we calculate atomic mass, or the entire weight of that atom, we don't even consider the electrons. We only look at the protons and neutrons. But those guys, that is how they're built. Now, there are two basic models that we're going to look at when we look at these things. Now, one important thing, I almost forgot about this, is that it's very, very important that we know. If you look at the periodic table, you'll know that the number of protons has to match the number of electrons. Now, that means that the element as it appears on the periodic table is going to be neutral in charge. It's neither going to be positive nor is it going to be negative. It's going to be neutral. And the only way that that is possible is if you have the positive protons an equal number with the negative electrons. They have to balance out. So we know that every time we find out how many protons are in an atom, we automatically know, all things being equal, how many electrons that atom is going to have as well. Now, these are the two models of atoms that we're going to look at. One is known as the planetary model. Now, the planetary model is simple, and there's a logical reason why it's called that. Well, because it basically is very similar to the way we look at our solar system. You have the sun, and then you have these electrons orbiting around the outside of the sun, or the planets orbiting around the outside of the sun. These electrons act very similar to planets orbiting a sun, except they are moving much, much faster, and they are not following a continuous pathway. These guys are switching up into many, many different pathways, constantly rolling over and past each other, moving at the speed of light at different loops. Now, these are known as orbitals. To orbit something means to go around it continuously. But these guys are going to follow what we call an orbital pathway. Now, if you look over here on the right hand side, you're going to see the orbital model. Notice that you don't see the electrons in this model, you just see kind of like a cloud. That's because we don't really know where the electrons are. We don't really know the pathway that each individual electron is taking. It's kind of very difficult to see because of the speed that they're traveling and the size that they are. So it's an estimation. You kind of guess where they are. In that sense, we know that they're there. We have physical evidence to prove that they're there. We've conducted experiments that show that we do have electrical particles coming off atoms. That's actually how we get electricity. So the evidence of them is there, but we can't really see them or track them very easily. So they just put this cloud around the outside and say this is the general area where these electrons are going to be found, and we call this the electron cloud. That is the orbital model. Okay? Now, if you look here, you're going to see how we identify different elements. It's important that we know that elements are identified according to the number of protons that they have in each element. Okay? Now, each element has a different number of protons. For instance, a hydrogen is always going to be a hydrogen as long as it has one proton. Helium will always be a helium as long as it has two protons. Same thing with lithium. It will always be known as a lithium as long as there's 3 protons. It's the number of protons that affect the actual type of element that we are dealing with. You can actually take away or give an extra neutron to an element, and it will not cease being that element that it already was. But if you take or remove or add a proton, you can actually change what the element is. If I give a new proton to hydrogen, it ceases being hydrogen, it becomes helium. However, if I add a neutron to hydrogen, it actually doesn't cease being hydrogen. It just becomes a different form of hydrogen. We will call that actually a H1. which is a isotope. And we'll talk about those here in a few minutes. Now let's talk about, we were just talking about how we identify the elements. And I already talked about the atomic number, but let's go back over it again. The atomic number is the number of protons that are in the atom, or that the atom contains. The atomic number is the number of protons that the atom contains. Now you're going to find this information on page 30 if you're turning in and following along in your textbook. Okay, so the atomic number is equal to the number of protons that the atom has. The atomic mass is the number, or the sum of the protons plus the number of neutrons. That's the atomic mass. That's the weight of it. Okay. Isotopes. Now, we already said that how we identify an element is based on the number of protons that element has. But what happens when we change its number of neutrons? Well, that's when you get an isotope. Atoms of the same element with the same number of protons and the same atomic number, they will sometimes vary in their atomic mass. That means they may either have more or less neutrons. That makes this particular element an isotope. Okay? That's an isotope. So it has the same number of protons but a different number of neutrons. That is what makes an isotope. Now, atomic weight. We already talked about this. This is affected when we're dealing directly with isotopes. Now, if you want to look over on page 31, I believe, is where we are. No, we're on page 30 still. Second column, second paragraph. The atomic mass of any atom is the sum of the masses and the protons and the neutrons contained in the nucleus. If you look on down, we're going to talk about how we're looking at, or how atomic mass or atomic weight is directly affected by these neutrons. Now, close to the mass number of most abundant isotope. What this is talking about here is something quite simple. When we're dealing with isotopes, when we're dealing with isotopes, it's important to know that we may deal with various different types of isotopes, but there's going to be some that are more common than others. And what happens on the periodic table, the atomic weight that is given, or the atomic mass that is given, is going to be closest to the most common way that you will find that particular element. Give you